Hi, we're going to continue with acid-base theory in the HL level for IB chemistry. And as we've been talking in class, I want to talk a little bit more about salt hydrolysis. And I just wanted to remind you, salts are normally formed by the neutralization reaction between an acid and a base. All right? So we have, and it does not matter what that acid and that base are, whether they're strong or weak. Neutralization is the point at which the concentration or the amount, the number of moles of H plus and the number of moles of OH minus are equal to each other. So basically is when you have equal amounts of acid and base that have been added together. All right, so that's when we get a neutralization. So when you're reacting a metal hydroxide as your base with an acid, you're going to get our familiar formula of salt plus water. In the case, for example, nitric acid plus calcium hydroxide will give you calcium nitrate, which is a salt, and it'll give you some liquid water. All right. If you're talking about a weak base, you then tend to have a formula that's a little bit more complicated, or sometimes a little bit different, because the salt that forms normally in solution is going to be both the conjugate acid and the conjugate base. It's going to be the combination of the two things, because it tends to be that the acid and the base become one entire compound. It may be easier to understand if we break the salt into its component ions, and so the base forms the conjugate acid, and the acid forms the conjugate base on this side. For example, when we react nitric acid and ammonia, we get ammonium nitrate. So we could break it into the ammonium ion and into the nitrate ion. When those are in solution, they separate. But it is nice to see that it's a slightly different structure, but it's the same idea. We make a salt when we react an acid and a base. All right. Now, salts can be formed by the combination of any pair of acid and bases. So you can have a strong acid with a strong base, a strong acid and a weak base, a weak acid and a strong base, and a weak acid and a weak base. All right, so we are going to analyze what are the effects on the pH of making any of these salts. Notice that it does not matter whether we made the salt in situ, all right, in place by the reaction of an acid and a base, or we just took the salt and we dissolve it into water. It is going to have the same results, because in a neutralization reaction, all of the acid and all of the base get neutralized, and so they're no longer present. You only have the salt. So it does not matter whether we made it by the product of an acid-base reaction or we just dissolve the salt directly in water. It is going to have the same effects on the pH. All right. So all you need to know is what the parents' acid and bases were, whether they were strong or weak acid and bases. Okay. So in the process of neutralization, we're going to look at the conjugate acids and the conjugate pairs that they make. So remind you, the conjugate of a strong acid is a very, very weak base. It's so weak, the conjugate base is so weak that it cannot hydrolyze water. The conjugate of a weak acid is relatively a strong base. It doesn't mean that it's really a strong base, it just means that it's strong enough to hydrolyze water and therefore affect the pH. The conjugate of a strong base is going to be a very weak conjugate acid, and therefore it cannot affect the pH. But the conjugate of a weak base is going to be relatively strong, and therefore the conjugate acid is going to be able to donate H plus into solution and affect the pH. All right, so let's start by looking at the first combination, strong acid with strong base. Remember, strong acid makes a very weak base, strong base makes a very weak conjugate acid. All right, and so in that case, when we have a strong acid and a strong base, the solution, the resultant solution, is going to be neutral. We are not going to affect the pH of that solution once the solution has been made. Once we have neutralized all of the acid and all of the base, we are literally going to be at neutral solution. If we're at 25 degrees Celsius, it will be a pH of 7, because we will have equal amounts of H plus and OH minus. All right, so that's an example of when we neutralize sodium hydroxide and hydrochloric acid, we make sodium chloride and water. the sodium ion is very, very small. It has a low charge. It does not have enough, it cannot act as a strong Lewis acid, and therefore it does not cause the hydrolysis of water, so it cannot affect that. The chloride ion is a very, very weak base. It does not want to revert by reacting with water to make HCl again, hydrochloric acid, because it's very strong acid, so it's going to be close to 100% dissociated or ionized, so it's not going to move in the reverse direction in any significant amount. Because this is so, there is no change in the concentration of the hydroxide or hydrogen ions, and therefore the pH remains at 7. This is going to be always the case for strong acid and strong base. So whether we take it and neutralize it, or we make a solution from a salt that was made from a strong acid and a strong base, if we take that salt, it will give us no change in the pH. If we instead have a solution of a strong acid with a weak base, all right, this will result in an acidic solution. It is not acidic because we didn't finish neutralizing. It's acidic because the conjugate acid of a weak base is relatively a strong acid, and so that's what's going to change the pH. The strong acid has been completely neutralized, but it makes, because it reacted with a weak base, the base is a relatively weak, a relatively strong acid. Let me rephrase that again. The strong acid is going to neutralize with the weak base. The weak base is going to make a conjugate acid that is relatively strong and therefore can affect the pH. All right, and that's what's going to cause this to happen. So let's look at an example. If we react like we did earlier, or we spoke about earlier, nitric acid with ammonia, we're going to make ammonium nitrate. Now, ammonium nitrate in solution dissociates into the ammonium ion and to the nitrate ion. The nitrate ion is the conjugate base of a strong acid, so it's going to be a very weak base and cannot affect the pH because it cannot hydrolyze water. Ammonium, on the other hand, is a conjugate acid, all right, of a weak base, and therefore is strong enough to be able to donate H+ into the water, to the solution, and therefore decrease the pH by increasing the acidity of the solution. All right? So if we wanted to find out the pH of a solution of ammonium nitrate, we need to find out what the concentration of that ammonium nitrate is, and then do an equilibrium analysis as usual. All right? So if I say, oh, the resulting concentration of ammonium nitrate is 2 molar, I can go ahead and do my usual analysis. I put my initial for the ammonium as 2, 0 for the H+, 0 for the ammonia. Why do I put that? Because I have to remember that ammonium is acting as an acid. What do acids do? And remember, we're talking about the Bronsted-Lowry definition. Acids are H+ donors. And whatever is left behind is going to be the conjugate base, or in this case the actual base, which is ammonia. And we just have to make sure that we don't forget that process. All right? And in this particular case, because it's acting as an acid, we don't have to include the water. We could include plus water, and instead of getting H+, we get the hydronium ion. But we're going to simplify our life and just write H+. All right? Now, there's no initial H+, there's no initial ammonia, there's only ammonium that is being dissolved. Why do we not include the nitrate? The nitrate is acting as a spectator ion. It is not reacting, and therefore it can just be eliminated from the reaction. Okay? The change, we're going to take some ammonium and break it down to make H+ and ammonia. Therefore, it's going to be -X, +X, and +X, as we have here. All right? So at equilibrium, we would have 2 - X for the concentration of the ammonium and the concentrations of the H plus and the ammonia would both be X. Now, in order to solve this problem, we need to know what the value of Ka is. Now, the value of Ka is not given to us, unfortunately, on table 15. All right, we look for it all over the place and we don't find it. But what we can find is the value of pKb for ammonia. And you will recall that pKa times pKa plus pKb equals 14 for a conjugate pair. And so if we have data for the bases, for the weak bases, we can calculate the value of Ka for the conjugate acid. All right, so we take the value. The pKb for ammonia is 4.75. We can calculate that the pKa then will be 9.25, and 10 to the negative 9.25 is going to be equal to the Ka, and that equals to 5.6 and 10 to the negative 10ths. All right, since that value of Ka is very small, we can see that this value here of 2 minus x is approximately going to be 2. All right, and I actually have written this down here, but I just wanted to make sure that you saw it. And we write, always remember to write your equilibrium expression. In the IB, you'll always get points for writing the equilibrium expression. So x squared over 2 is equal to 5.6 and 10 to the negative 10ths. When we do the math for that, we get that x is equal to 3 times 10 to the negative 5th, which is equal to the concentration of H plus ion. We take the negative logarithm of that number, and we get that the concentration, sorry, that the pH for this solution that was 2 molar in ammonium nitrate is 4.48, which is quite acidic, and we don't have any strong or weak acids. We could have actually have that be the result of a neutralization reaction, and it still would have given us that value. All right, wonderful. So let's look now what would happen if we have instead a weak acid and a strong base. As you may notice, well, it says it very much in the top, but if you may notice from the previous one, if the strong acid was reacting with a weak base, you're going to get an acidic solution. Now, when we have a weak acid acting with a strong base, you're going to get a basic solution. Now, it'd be, again, an error to think that it's because we're left over with some strong base. If you have the right number, the stoichiometry, the right number of moles, there's going to be none of the weak acid and none of the strong base left over. You're only going to have the salt. But the salt is composed of the conjugates. The conjugate of a strong base is a very, very weak acid, so it will not have any effect. But the conjugate base of a weak acid is a strong enough base to affect the pH. All right? And so let's look at an example like this. In this particular case, we've got an acid such as propanoic acid. I decided to use a different acid so it wouldn't get too boring using ethanoic all the time. Propanoic acid is a weak acid and is reacting with a strong base, potassium hydroxide, to give you potassium propanoate and water. Now, potassium propanoate breaks into the K plus ion, the potassium ion, and the propanoate ion. Now, the potassium ion is a very weak acid. It has only a charge +1, so we know that charges of +1 don't tend to cause hydrolysis of water, and so we're not going to see it acting as a Lewis acid. But the propanoate is the conjugate base of a weak acid. It's strong enough that it can cause the hydrolysis of water, hydrolysis of water to release hydroxide, all right? And if it releases hydroxide ion, we are going to increase the pH and make the solution basic. All right? Now, how do we do this? If we know the concentration that we end up with of the potassium propanoate, we can find out our pH, again doing equilibrium analysis. So let's take that into consideration again. If we have an initial concentration, if we find out that the concentration of the potassium propanoate is 1.5 mole per decimeter cubed, well, we have to be able to see this equation. And again, this is where our concepts are going to be tested. We need to remember, how does a base react, a weak base react? It needs to react with water. All right? Now, I haven't written it there, but you can see that the water is a pure liquid and the other ones are going to be aqueous in solution, and therefore they go into the equation of Kb, all right? But we are not going to include the water, all right? We set up our concentration. We put their concentration of the propanoate ion as being 1.5, and our concentration of the propanoic acid and the hydroxide ions being just 0. As it changes, you consume some of the propanoate to make propanoic acid and hydroxide, all right? And so at equilibrium, the concentration of propanoate will be 1.5 minus X. The concentration of propanoic acid will be X, and the concentration of OH minus is going to be X. And that is the concentration that we're interested in. We're actually not interested in the other concentrations because they don't go into our calculations of pH or pOH. Now, we will need the other concentrations, but this is the one that we focus on. Now, what is the value of pKb for propanoate? If you look at it in here, you cannot find it again, but you can find the value of pKa. If you look, all right, you can find the value of pKa for propanoate, which is 4.87, and from that we can calculate the value of Ka for there's a typo there. They should say the value of pKb, all right, for the propanoate ion. Remember, pKa plus pKb equals 14. So 14 minus 4.87 is going to give you 9.13. When we do 10 times 10 to the negative 9.14, is going to give us 7.4 times 10 to the negative 10ths. Again, a very small value, but it is going to be basic enough to affect the pH. Because the value is so small, 1.5 minus X is going to be approximately just 1.5, because the value of X is going to be so small that it gets lost in the decimal places. We write our 3 points, the expression, the equilibrium expression for Kb. It's the concentration of the propanoic acid times the concentration of the hydroxide ion divided by the concentration of the propanoate ion. X squared over 1.5. I don't know why this moved, but it did. X squared over 1.5. And that's going to be equal to our equilibrium constant Kb, 7.4 times 10 to the negative 10. When we calculate the value of X, we basically multiply 1.5 times 7.4 times 10 to the negative 10 and then square root it. We get that the value is 3.3 times 10 to the negative 5. All right? And that's going to be equal to the concentration of the hydroxide ion. All right? Now, the concentration of the hydroxide ion does not allow us to calculate directly pH, but we can calculate pOH. Negative logarithm of 3.3 times 10 to the negative 5th is 4.48. And then 14 minus 4.48 gives us the pH of this basic solution, which is going to be 9.52. The most common mistake that students tend to make in this type of problem is that they get the answer of X and they move on. They forget that the question always asks them about pH, pOH, or something like that. And so it is important to keep in mind how far or where you're going to in your actual work. Okay, so please keep this in mind, and we will carry on. Okay, what happens if we have a weak acid and a weak base? Well, your bet is like as good as mine. Actually, the reality is you have to compare the strengths of the acid and the base to see whether it's going to be acidic, basic, or a neutral solution. If both the weak acid and the weak base have very similar values of Ka and Kb, the reaction is going to be neutral because they're going to cancel each other out. But if the Ka of the conjugate acid is larger than the Kb of the conjugate base, the reaction is going to be acidic. If the Kb of the conjugate base is larger than that of the conjugate acid, the solution is going to be basic. And like I said, if the Kb's and Kas are equal to one another, then the reaction is going to be, or the solution is going to be neutral. You could do it by just looking at the weak acid and the weak base. You don't even have to look at the conjugates. If the weak acid is a stronger acid than the weak base, the solution is going to end up being acidic. If the weak base is stronger, has a greater value of Kb, then it's going to be basic overall. So you have to compare those, and you have to be looking at those numbers, and be very careful, because when we're dealing with values that are 10 to the negative something, it is always going to be difficult. You have to think which one's larger, which one's smaller. All right. You can also do it by comparing the values of pKa and pKb. Remember, the smaller the pKa or the pKb, the stronger the acid or the base. So you have to do analysis of this form. Okay. So that's that part. There's only one final thing that I want to talk to you about, and it is what happens if we have the salts of highly charged metal cations. If you have highly charged metal cations like aluminum, like magnesium, all right, like chromium or titanium, you're going to make acidic complexes, because the metal cation is going to act as a Lewis acid. It's going to coordinate waters around, and those waters can have their H's broken and released as acid. So for example, in the case of the aluminum ion, and we talked about this when we talked about in unit 3 about periodicity, and we were looking at the elements in period 3, we talked a little bit about this particular effect. But aluminum 3 plus ion actually forms a hexacoordinate complex with 6 waters around it, and those waters can lose H plus to then form some hydroxide, and notice that the charge of the ion then starts decreasing, because you're increasing the amount of concentration, or you're increasing the concentration of the H plus ion. The pH of the solution is going to go down. All right. Now this is just a small curiosity that I wanted to show you. You can continue to deprotonate the aluminum, the hexaaquo aluminum 3 ion. All right. By adding more and more base. All right. And initially, if you deprotonate it 3 times, it's going to precipitate and form this solid. But if you continue to add more and more ammonia and continue to deprotonate, what actually happens, it's only a solid when the overall charge is 0. It then redissolves when the charge becomes negative, and you have the hexahydroxyl aluminate ion, because now we have a negative charge. Do not worry about this. This is just a little bit more to show you that. So with that, we're going to stop here, and we're going to talk about buffers in the next video.